What's cooking, babes? Brought to you by Damon. Okay, so we're here today looking at thermodynamics. Specifically, we are looking at the gas laws. Now, you may have talked about these in the world of chemistry before. Chemistry. But they're worth bringing up again because we're going to need this ideal gas law in order to work problems out in the world of thermodynamics for whenever we get into heat engines. And it's a very, very important idea there. So, if we have three different terms here, pressure, volume, and temperature, it's worth trying to think about how these three things are related to each other when different effects are changing. So our first thing that we can state in terms of these three variables here is that when the pressure is constant, your volume is going to be proportional to the temperature. And this is when the pressure is constant. We refer to this as Boyles Law. Now, a great example of when the pressure could be constant on an object, but your temperature and volume are increasing, would be if you had some sort of something kind of like a balloon, not exactly like a balloon, but something very similar where you have an elastic surface that as you blow into it, as you put more matter in there, you'd think you're increasing the pressure, but you're not. It blows up a little bit. Your volume's increased. And if you actually took that balloon at some pressure and you heated it up, the molecules in there would be moving around faster and faster and faster, which we'll talk about later. And as a result, that balloon would actually begin to expand because of that temperature increase. So the pressure would be constant there, but the volume would increase because the temperature would increase. Now, another relationship that we have here is that the pressure, that's a janky looking letter P, pressure is proportional to temperature. And this is true when the volume is constant. This is referred to as Gay-Lussac's law. My class is commenting this sounds familiar because this came from chemistry, and they've all taken chemistry before.
Chemistry smells.
Naturally, they all think chemistry smells, so they've all, while it might be familiar, it's something to remember. Pressure is proportional to temperature when volume is constant, and this is easy to remember due to a can of beans. What? If you take a can of beans and you set it on a fire, and you just wait, get behind a barrier, because that can of beans is going to explode. If you don't let the buildup of pressure release, it's going to blow apart your can of beans. So we see here that pressure is proportional to temperature. As the temperature goes up, the pressure goes up as well. This is different from Charles's law, where as that temperature increased, the pressure was the same because we allowed the volume to expand. For the can of beans in that rigid container, its volume isn't changing. The pressure is just building up in there until it explodes. So we've got Charles' law, we've got Gay-Lussac's law, and our final one. We can state that volume is inversely proportional to the pressure. This is Boyles' law. And this is assuming, once again, that something needs to be constant. In this case, the temperature is a constant. What this is implying here is that if your temperature is constant, if you decrease the volume of something, you're going to increase its pressure. If you increase the pressure, you are decreasing the volume. Or if you increase the volume, you'd be decreasing the pressure. This makes a lot of sense anytime you have a half-finished bottle of water that you then all of a sudden like try to crush. When you try to crush that bottle, or that empty bottle of water, you can crush it a little bit because air can be compressed, but as you begin to compress it, you're decreasing the volume, you're beginning to increase that pressure on that plastic bottle of water. So that's what's going on there, assuming your temperatures are constant. So that's Boyles' law. Now, while each of these are powerful in their own right, None of them alone is what we want here. What we actually want is something a little bit more advanced and sophisticated. If we take all three of these and we put them together, we notice that both pressure and volume are directly proportional to temperature, and that the volume is inversely proportional to pressure. So this means that if we were to kind of write this out mathematically, pressure and volume have to be on the same side of the equation, and they would have to be equal to some unknown term here, right? Like some possible coefficient or something multiplied by some temperature. There could be other stuff here. There could be a whole slew of other things, but P and V have to be on the left, and then something T has to be on the right. In terms of the gases we're talking about, this is some amount of gas here. And the way we talk about this amount is we end up saying that PV equals N, this is a little n here, capital R, and then the temperature. PV equals nRT, or as we'll commonly call it, PivNert. This N here stands for the moles of a substance, and you might recall that term from chemistry. R is an ideal gas constant. The value we are going to use for R in this class is what I refer to as 8.pi, because that value is going to be 8.314 joules per mole Kelvin. And technically, if you wanted to put per, so we're going to say joules per mole Kelvin here. This temperature, we need to be careful because this temperature is measured in Kelvin here. We'll see later on, we might have a delta T in here instead, in which case it doesn't matter if it's Kelvin or Celsius for the delta T's. We've discussed that before, they're on an absolute scale. But in general, we will be using Kelvin here. And that means that we need to recognize a way to convert between Celsius and Kelvin. If you want to go from Celsius to Kelvin, you may recall this. You'll simply take your temperature in Celsius, whatever number that is, and you'll add 273.15, but who cares? And that will give you your new temperature in Kelvin. So 0 degrees Celsius is 273 degrees, or 273 Kelvin. You actually don't say degrees Kelvin, it's kind of redundant, but that is what we have there, okay? Some other helpful things in terms of this ideal gas law are you probably, if you're a true at heart physicist, may have forgotten what a mole actually is. This N here, moles, we need to remember that it stands for a mass divided by a atomic value. And what we can think about there is its mass divided by its atomic mass in that case. We'll talk more about this later on in the year. Whenever we do problems, we are more than likely going to be given the number of moles here. So we really don't need to worry about this stuff. If you're a chemist and you're like, oh, let's get into a more derived definition of the moles, find a different video to watch, because this is not the video for you. Okay? We really just skirt chemistry as much as possible. What we can see, though, in terms of the physics side of things, is that over here, with this value of R being joules per mole Kelvin, the moles are going to go away because of the N values, and the Kelvins are going to go away from the temperatures. But that means that on the right here, nRT is actually equal to a joule amount, which is a unit of energy, which means that this PV on the left-hand side, that's also a unit of energy, which is a really weird idea, but it's something that's going to drive thermodynamics and why we even have this entire branching subject in physics to begin with, okay? So for now, that is the ideal gas law. This PivNert, PV equals nRT. This is something you must remember, and it's a very important thing here. If you want, you actually don't have to use Pivnert, though. Maybe you remember this little term here, Na. This is Avogadros number, often called Avogadros number in this class. This is 6.022 times 10 to the 23rd molecules per mole. What you can do with this is you can actually switch the Pivnert equation. Instead of talking about moles of some ideal gas, you can talk about how many molecules of that ideal gas exist. In doing so, this equation changes slightly. You're still going to have PV, but now you're going to have capital N, where this capital N is actually the number of molecules. And instead of having this value R, you're going to have the value K, where this K here is referred to as Boltzmann's constant. It has a value of 1.38 times 10 to the negative 23 joules per Kelvin. Technically, it's like joules per molecule Kelvin, but, you know, the molecule goes away. And then there's the temperature tacked onto the end here. Okay? Sometimes in the world of physics, we're given the number of molecules, in which case it's easier to use this equation. Sometimes we're just given the number of moles, and it's easier to use the Pivnert equation. It doesn't matter which one you use. Nobody cares. But the way they are linked is through Avogadros number. And that's because that ideal gas constant R divided by Avogadros number, that is Boltzmann's constant. So all we're doing here is we're switching these moles out for molecules. We're redefining a constant to get K, and it's this exact same equation. So no matter which one you want to use, it does not matter. You're going to get the same results no matter what. Okay? So with that, this introduction to the ideal gas laws, Pivnert right here, very, very important, and the PV equals NKT if you'd like to use that, is finished. In our next video, we're going to take this idea of ideal gases, and we're going to actually take a gander of how they're actually moving around and bouncing off each other for a rather long derivation for the kinetic molecular theory of matter. But until next time, adios, and take it easy.